Hello, everyone. My name is Ege. I'm from the University of Oslo, and I'm here to show some of my preliminary work I've been doing over the last year. First, I will describe a bit about what I'm doing and what research question I am focusing on, and then show the methods I'm using, show some results and some points for discussion and future work that might be good. We've had a lot of talk about morphology and brain co-optimization and about learning. So my introduction is going to be very similar to that, but maybe it's described in a bit different way so you know how I'm thinking about it. So a robot consists of two optimizable components, which is the morphology or the body of the robot. And you also have the control, the brain of the robot, which controls the robot. And the challenges here are basically that it are two different search landscapes, and this often turns into early stagnation. So how that might work is, let's say you have a parent robot and that introduces two different robots. The top one is an offspring robot, which is very similar to the robot and therefore has a very close to optimized control if you take the control of the parent robot. So it performs better due to matching control of the parent robot. And let's say that the bottom robot is potentially better than the first offspring robot. It requires a completely different control. So in this case, it would be discarded because it's not performing as well as the first robot. And this is how early stagnation will happen, because it will keep picking robots that are similar to robots that are already existing, because it is closer to the control. So one other way to see this is fitness landscape. So let's say you have the morphology search space on the horizontal axis and the potential performance of the morphology in the vertical axis. You start with the parent robot there on the left, and then you get the potentially better performing robot on the right. But because its control is not optimized, the actual performance will be worse and therefore discarded. This is a well-known problem, this local and global optimum problem in evolutionary algorithms in general, but this non-optimized control, it adds another challenge, because even though you have a better morphology, it will still perform worse. And a solution to this is to add a lifetime learning loop to the morphology of the robot. So robots in this case are evaluated with multiple controller settings. So in that case, the top robot, which is potentially better than the bottom robot, will have more tries to get a better performance and therefore more likely to be chosen. This has shown to work quite well. So in some previous work, comparing learning to non-learning robots, it shows that in this case, the red line is, the green line is without learning, and the blue line is with learning, and it's the performance after learning. With learning, it performs better. But it also depends on how you compare it. In this case, it's compared over generations, or as I maybe would like to say, over total number of morphologies evaluated. And this makes a lot of sense if you evolve in a real world, where creating a robot is a much higher cost than evaluating a robot. Like as in the previous talk, where making a robot might be half a day or a day, and evaluating is maybe, I don't know, 1 minute, 20 seconds, or even shorter, but not 1 day. In virtual environments, this might make less sense, because creating a robot in a virtual environment takes maybe a millisecond, while evaluating one, in the second. So in that case, it would make more sense if you would compare it on function evaluations instead of generations or morphologies tried. And in that case, it also depends on whether you want to compare with the best robot or the mean robot. But for example, looking at the left part of it, left figure at the bottom, it is compared over function evaluations, and it's the mean fitness of the populations. And there, the evolution only performs actually better than the evolution plus learning. In the right figure, it is that the evolution plus learning performs better. In that case, the max fitness is chosen instead of the mean fitness. But what I would like to show here is that, yes, learning performs better, but it also depends on how you compare. And I understand comparing on morphologies tested makes a lot of sense. What I would like to add with my research is as well what the influence of environment complexity to the learnability of robots is. Because let's say you have a very easy environment, you might not need that many learning trials to get well performance. With a harder environment, you might need more learning, or said otherwise, maybe for a very easy environment, you don't even need learning at all, and any control scheme might work for the right robot. So I wanted to look into how the environment complexity influences the learnability. So now over to the methods I'm using. So I'm using a modular approach where there are 3 building blocks. Every robot has at most and at least, so exactly one core robot, one core module. And there are blocks and joints that can be added to the robots in a 3D grid. I am using direct encoding. So the robots are just this picture, for example, and it's just directly encoded into this. You create a robot and you can do certain mutations or crossover to it. Mutations are to add a module to it or multiple modules, or to remove modules from the robot. So let's say you want to remove this module. It doesn't mean that only this module gets removed. This module away from the core module gets removed. So if you would want to remove this module, all these modules get removed. Those are the 2 mutations that are possible on the robot morphology. A crossover happens from the direction of the core module. So you have 2 parents and you select randomly a direction from the core module. Let's say from the right robot, the right part is selected, and the top robot, the top part is selected. These modules are swapped to create 2 offspring robots. This is the morphology. The controller is a sine wave, which has certain learnable parameters. And it takes also as input a touch sensor. So every hinge of the robot has a touch sensor, which senses whether it touches the ground. And there are 5 learnable parameters. One is the amplitude of the sine wave. One is the phase offset. And you have 2 weights for the touch sensors. One is if its own touch sensor touches the ground. The other is if a neighbor touch sensor touches the ground. And a phase offset for this touch sensor. So the results we're going to look at now work with these equations, but they are not that good. For example, actually these need to be removed, because this way you can have a double touch sensor. If your own touch sensor and a neighbor touch sensor touches the ground, it will basically do the same thing twice. So that is something that will improve later, but the results you will see is with the control without the red lines. So in my case, there are a certain number of controllers for the robot, which each hinge can basically choose from. So you have, for example, 4 controllers, and controller number 1 controls the hinges it points at, and so it controls 2 hinges in this case. This is randomly chosen. It's not chosen by me. And in this case, for example, controller 4 controls nothing yet. But if you add a hinge during mutation, for example, it will choose one of the 4 controllers randomly. And I have talked about 2 mutations for the morphology. There's also 1 mutation that is possible for the controllers, which means that the controllers will just switch which hinges it are controlling. So for example, this can happen that first the controller 2 controls the bottom hinge, but it will control the left hinge. So those are the 3 mutations. So I talked about what the crossover was. The initial number of modules is between 5 and 10. The 3 mutations are to add modules, remove modules, or switch controllers. There's a maximum number of modules added during mutation of 5 as well as removed. And when they're switching controllers, there's a 50% chance that the controllers will be different per hinge. So per hinge, it will have a 50% chance of switching controllers. And this is the evolution overview of my method. So you first initialize a certain number of robots, and this goes through a certain number of controller learning trials. And once this is done for all robots, the crossover mutation and selection is done. And this will go on until I tell it to stop. The learning algorithm in my case is Bayesian optimization. I chose this because the number of controller parameters to optimize in my case is not that much. So Bayesian optimization works well in this case. And yeah, some parameters are chosen for this, which are chosen fairly regularly in evolutionary robotics. And an overview of the evolution parameters. The most important ones here is that there are 2 environments. One is the flat environment, which in my case is the easy environment, and the hilly environment, which is the more challenging environment. There are 3 learning budgets, which is 1, which is basically no learning, and 30 and 50. So 30 learning trials or 50 learning trials. And the objective is just forward movement. So the fitness function is just move as far as possible. The results show that indeed, if you compare morphologies evaluated or generations, the learning performs way better than without learning. So that's no surprise. But if you compare on function evaluations, the differences are smaller. But more importantly, the difference become bigger the harder the environment is. So at the right figures at the top, you see the flat environment, which shows not that much difference after 100,000 function evaluations. However, in the hills environment, both the learning situations perform quite similar, but without learning or a learning budget of 1, the performance is quite worse than the others. And also some figure which shows something related to the learning delta, which is indeed increasing in my case as well. So this shows for all the 4 situations. So on the left, the learning budget of 30, and on the top, on the right, learning budgets of 50, and on the top, flat environment, and on the bottom, an hills environment. The darker the line gets, the later it is in the evolutionary process, and you see that even though the initial performance is also increasing over generations, the difference between the beginning and the end, in this case the learning delta, is also increasing over generations. So this is another way of visualizing that there is an increasing learning delta over generations. I wanted to show some videos, maybe one. This is one of the robots that comes out with without learning. So on the flat environment, I basically saw 3 types of morphologies, movement patterns. One was the one you just saw. This one uses two limbs kind of to move forward. And there's also a rolling pattern. But I would also like to mention that I did not do any quantitative analysis about it, but looking at it myself, I didn't see much difference between the morphology when you learned or you didn't learn, or there was a hilly environment or a non-hilly environment. The performance was quite similar, actually. Some final discussions, so some improvements. I want to improve the controller mechanism, as I mentioned before. One thing that also needs to be done is an evolutionary search for the controller without learning. So without learning, actually, there is no evolutionary search for the controller, so it just picks a random set of controller parameters, which might not be as fair to compare it to something that can learn. And maybe to add it as well for a higher learning budget so that you can transfer samples in the creation optimization, which might resemble some Lamarckian controller inheritance if you want to learn the best performance out of the parents. And maybe some more function evaluations, because if you look closely, you can see that the blue and red lines in this case still seem to be a bit more improving than the green line, which is the no learning budget. So if I would have compared over 200,000 function evaluations, I might have said something completely different. More challenging environment, of course. So at the left there are the two environments I chosen, but it can be more noisy, or instead of hills, it can be steps so that it doesn't just fall down a hill and then continue moving. And I want to reiterate, how do you compare? So do you compare over morphologies evaluated? Yes, learning performs much better. Do you perform over function evaluations? Depends. Also depends on whether you compare on mean fitness or max fitness. Depends on what you want from your system. Thank you for your attention.